Have you ever wondered why an antenna's receiving behavior has the same angle dependence shape as its transmit radiation pattern? It kind of seems intuitive that it should do that, but why? It's actually because of a property of Maxwell's equations called reciprocity, which says that if you take this situation where you have one antenna transmitting and another antenna receiving, it is the same as if you put this source over on the other antenna and had your formerly transmit antenna receiving while your formerly receiving antenna is transmitting with the same voltage source and everything. That is reciprocity in a nutshell. If you want to hear about why this is so, I am about to do a whole derivation using Maxwell's equations, but honestly, if you are willing to accept this fact, you can stop now. The result that we get to in the end is that the power received over here is equal to the power received over here, if this is a reciprocal situation. In order to obey this reciprocity relationship, all we need is for the antennas and the antennas' impedances and anything in the medium in between the antennas to be passive and isotropic. And that's it. And then if that situation is true, you have reciprocity. Like I said, you can stop here if you don't want to go any further, but if you do want to know why this is true, I'm going to start with Maxwell's equations and do a little bit of explaining. We start with a vector identity, and that is that the curl of the dot product of two vectors, A and B, is equal to the curl of A dot B minus A dot the curl of B. We're also going to use Maxwell's equations. Faraday's law, so the curl of E is equal to minus J omega mu H minus M. That's a magnetic current, which doesn't exist in real life like we've talked about, but it can be a useful problem simplifying tool, so we're keeping it. And we've got Ampere's law, curl of H is J omega epsilon E plus J. And as you know, that's an electric current. The way reciprocity works is we start by setting up two separate problems. In problem 1, we have sources J1 and M1. And in problem 2, we have sources J2 and M2. Which means that in problem 1, we have electric field 1, E1, and magnetic field H1. And in problem 2, we have E2 and H2, like that. And the whole reciprocity theorem is all about the relationship between these two problems, these two sets of different sources and different fields, which can exist at the same time. You could have J1, M1, J2, and M2 all on at the same time, or you could have one set of sources on and the other set of sources off. Either one could be relevant to the situation. Now, we apply all of those vector identities to Maxwell's equations in order to get the Lorentz reciprocity theorem, which is, in differential form, minus the divergence of E1 cross H2 minus E2 cross H1 equals E1 dot J2 plus H2 dot M1 minus E2 dot J1 minus H1 dot M2. We're going to put this into an integral form, so we're going to do a volume integral. And then we're going to apply the divergence theorem to this divergence right there. So then what we get is that minus the surface integral of these two cross products, E1 cross H2 minus E2 cross H1 dot ds is equal to a volume integral, and obviously the surface integral happens over the boundary of that volume, E1 dot J2 plus H2 dot M1 minus E2 dot J1 minus H2 dot M1. Nope, minus H1 dot M2 dV. Okay, how is this useful? There are a few different ways that this can be useful in an electromagnetic context, but specifically for antennas, what we like to do is let the left-hand side, the surface integral, be evaluated over a sphere of infinite radius. And obviously the volume integral has to be doing that as well. So let's say V is a sphere and let its radius go to infinity. In that case, this surface integral here goes to 0 as long as the sources are finite sized, which all sources are. And then we're left with that volume integral which is equal to 0. More often, we express this as two halves of one problem. So we'll say the volume integral of E1 dot J2 minus H1 dot M2 is equal to the volume integral over the same volume of E2 dot J1 minus H2 dot M1. What does this mean in practice? Consider, let's do a really simple example, two antennas. We're going to make them be dipoles. And we're going to make them be PEC dipoles. Let's put a current source on each one. So we've got I1 here and I2 there. If we evaluate this expression on each side, what we end up with is that this integral over the volume that contains the sources of E1 dot J2 There's no magnetic sources, so H1.M2 doesn't contribute anything. It's just going to turn out to be I2 times a line integral over the width of this gap of E1 dot dz, let's say this is all z directed. So we got I2 V1 because that's how you calculate a voltage. Well, I believe actually we'd have a negative sign there. If we did the same thing on the other side, oh, and although there are electric currents that exist on the body of the antenna, the electric fields themselves are zero on the body of the antenna because the antenna is a perfect electric conductor, and the tangential electric field on a perfect electric conductor is zero. So there is no E dot J there because the electric field equals zero on a PEC. So we're only really caring about the gap, just the gap. If we do the same thing on the other antenna, E2.J1, we get the same result. We end up with I1 times this integral of E2 over the width of the gap, which works out to be minus I1 V2. And I'm going to rename these voltages now, because it's not just V1. This is the voltage at antenna 1 due to this is the voltage at antenna 2 due to an excitation on antenna 1. So that's going to be V21. And the same thing over here. This is not just V2. It's going to be V12, which is the voltage at antenna number 1 due to a current at antenna 2. So that's why we have V12 there. So what we've gotten right now is that these two products are equal. I2 V21 is equal to I1 times V12. Remember, this is voltage at 2 due to a current on antenna 1, and this is the voltage at antenna 1 due to a current on antenna 2. So we can define a mutual impedance. To describe this situation. So we can say that V21 is equal to some impedance Z21 we can say that V21, this voltage at antenna 2 due to current 1, is equal to some impedance Z21 times I1. And we can say that V12, the voltage at antenna 1 due to current number 2, is going to be some impedance times I2. And we're going to name that impedance Z12. What reciprocity says is this product of that voltage and that current are equal, which means if we expand it out, I2 times I1 Z21 is equal to I1 times I2 Z12, or look, these current terms are the same, so Z21 is equal to Z12. That's what reciprocity gets you. And it has many implications, but for antennas, the most important one is the fact that the radiation pattern on transmit is proportional to the effective area on receive. And in fact, the way you derive that proportionality factor depends on the existence of reciprocity.